All right, good afternoon, everybody, and welcome to the March 2016 Agricultural Robotics and Automation Technical Committee webinar. This is our webinar number 36 in what is now the fourth year of the webinar series. And today we welcome Jeff Hollinger from Oregon State University, who is going to present his and his group's work on Bin-Dogs, self-propelled platforms for bin management in orchards. Bin-Dog is an idea that has been in a lot of people's minds, even here at Carnegie Mellon. We've talked about Bin-Dogs for a number of years based on input from actual growers, actual orchard owners who have to spend a lot of time and money placing bins in rows of orchards for the harvest. And not only the actual logistics of putting those bins in the rows is somewhat painful, perhaps even more painful is coming up with the right number at the right time. You put too many bins and you're wasting time. You put too few, and now workers, pickers, they don't have a bin to put their fruit in. And both of these have economic impact on the life of an orchard. And these growers would love to have, this is what we heard when we were working with agricultural robotics at CMU, these farmers and growers would love to have bins that are self-propelled, that you could simply tell them, you go in this row and you go in that row, and they would coordinate amongst themselves and, in fact, find the right places and the right rows to be at the right time according to what's being harvested in each row in each day. And Jeff is one of the people who is going to make that a reality. He is developing, in fact, these Bin-Dogs, and we're going to see some very cool videos today of how that is coming along. Jeff, more than just, quote-unquote, just a professor at Oregon State, he's a friend. He is a graduate from the Carnegie Mellon Robotics Institute. He is very well regarded here at Carnegie Mellon as having been one of the smartest, most successful PhD students in the Field Robotics Center, working with Professor Sanjeev Singh. And after getting his master's and PhD at CMU, Jeff spent some time at USC working with underwater robotics. But truly his forte and what he is known for, at least to us, is that Jeff is an expert in multi-robot coordination. And again, Bin-Dogs is not only about the wheels and motors that move those bins, but especially about how to coordinate among hundreds of bins in a farm to go to the right place at the right time. So Jeff, after finishing his postdoc at USC, got a professorship position at Oregon State, and where he's now developing a variety of robotic systems that are related to distributed coordination, learning in various domains, aerial, marine, and ground robotics. So Jeff, with that, let me pass the presentation rights to you.
Okay.
And everybody should now be able to see Jeff's slides. We are good on my side here. I'm just going to ask everybody to, again, please mute your phone or mic. I'm going to mute my phone now. And Jeff, thank you again for presenting today.
Okay, great. Well, thank you, Marcel. You made me blush a little bit with that introduction, but very, very happy to be here and very excited about the invitation to give this webinar and speak to this group. So this is a National Robotics Initiative project that I'm going to be talking about today, which was funded by the USDA part of the National Robotics Initiative. And I'm one of the 3 PIs on this project. Chin Zhang is the lead PI from WSU Center for Precision Agricultural Systems, and Matt Taylor at Washington State University is also on the project. So this is a Pacific Northwest collaboration where my group at Oregon State University is also collaborating with the Washington State folks to try to develop this technology. And so As Marcel already mentioned, what I'm going to be talking about is this Bin-Dog idea, which is a self-propelled platform for bin management in orchards. So what does that mean? Well, the motivation for what we're doing here, there we go, is apple harvest in Prosser, Washington. And so this is where we're developing the platform at the CPAS Center there. And so just to put what Marcel introduced in pictures, we have these rows in these orchards where there are a number of apple trees. And what we want to be able to do is we want to be able to manage the bins that the workers put the apples in. And so here you see sort of the traditional approach to doing this, where there's a gentleman in a tractor vehicle that is carrying this bin around. And so a number of folks go and drive these tractors around and place the bins, and then also pick those bins up when they're full. And so there's a picture of a bin in the middle of the lane. And so during harvest time, the pickers will take the apples and put them in the bins. And as the bins get full, what needs to happen is those tractor needs to come along and pick them up. Now, and then eventually take them back to the depositing station where they're then processed. Now, the issue with this is that this is not really a very efficient process. There's no way to optimize this process. Like Marcel was saying, if you put down too many bins, then you can run into situations where there are places without bins and other places have too many bins. If you don't put down enough bins, then the workers have to wait in order to continue picking. So you can lead to some fairly substantial inefficiencies here if you're not doing the bin management correctly. And so the motivation behind this Bin-Dog idea is that let's roboticize this, let's automate this, because harvest is very labor intensive. It's dependent on seasonal labor, as the folks on the phone, I imagine all of you know, and these labor costs are increasing dramatically. So the preliminary studies here were that there's actually the potential for up to a 50% productivity increase by using automation in this domain. And the reason that this number came about is because it turns out that about 1/3 of the worker time is spent idle because either they have a full bin or they need to pick in areas where there's not a bin and walk back, and those kinds of things really detract from the harvest efficiency. So there's real potential here to improve the efficiency of harvest, which is then, of course, going to save the growers quite a bit of money. So the main goal here from a robotic perspective, and so here's one of these videos that Marcel was talking about. So what we want to do is we want to develop an intelligent bin managing system that is supported by a robotic or multiple robotic self-propelled fruit bin carriers. And so this is just an initial video of the Bin-Dog platform. Let's play that again, turning into a lane. And so here you see this is a robotic vehicle that has four wheels. It's a gas-powered engine, and I'll talk more about the hardware as we move forward. But it's carrying along this bin sort of in the middle of the vehicle. It's not like a forklift design, so it is actually a fundamentally different hardware design than the kind of stuff that you see in the orchards today. And it allows us to do a number of really interesting things in terms of modifying the way that we do bin management. And so because this is a collaborative project and this is a robotics project, the technologies that we're developing extend beyond the hardware platform. The hardware platform is very interesting and novel, but there's also more to do in order to get this system up and running and be able to take full advantage of it. So the key technologies that we're developing are in mechanical design, so that's the platform design, but also in orchard navigation. How do we navigate in these lanes? How do we navigate in these headlands so that we can autonomously move through them and also interact with the growers in a situation where we don't want to cause any kind of danger to the growers or even add stress to the pickers situation. So what we're looking at is we're looking at in-orchard navigation. We're also looking at multi-agent coordination because we want to have more than one of these bin management robots. If we have very large orchards with potentially hundreds of rows, then one bin manager is not going to be enough. And so we want to think about how do we coordinate multiple vehicles, how do we optimize these vehicles so that we can improve the efficiency of the harvest. Also looking at human-robot interaction, as I mentioned, how do these vehicles interact with the pickers? Is there something that we can learn about different groups of pickers to try to figure out how to improve this optimization? So again, getting into how Apple bin management is done currently. So here's the current forklift model, just to give you a bit more information about that. So the first step is the tractor will drive into a lane and place an empty bin in that lane. And then once that bin is full, it needs to drive out of that lane. Because of the forklift model, it has to drive out basically the same way that it came in. Can't go over the bin. And then once that bin, it'll perhaps place some additional bins, and once a bin is full, it will come and pick that bin up and then take it back to the depot station. And so the kind of tasks that we need to automate here with the traditional forklift tractor, we have empty bin loading, where they're at the depository and want to take some bins out into the field. Half full bin repositioning, which is an interesting one, whether we should take bins that are not full and move them to other places because maybe we've picked all of the apples at that point. And then also full bin transportation. Once the bins are full, we want to be able to take them back to the repository. So how do we do this with the Bin-Dog autonomous vehicle? Well, what we did was we designed actually sort of a fundamentally different way of doing this. And so the bin management with the Bin-Dog, rather than having this drive into the lane, put the bin down, drive out, and then come back, here the Bin-Dog is actually able to go over the bin. So it's able to drive over full or empty bins so that it doesn't necessarily have to exit the lane the same way that it came in. So it loads an empty bin in the collection station, drives into the lane until it reaches a full bin. It can then drive over that full bin, unload the empty bin, and drive back to load the full bin. So it can do all of this at once. Basically, it can do bin replacement all in one go at the lane. So even straight off the bat, by redesigning the hardware itself, we're already able to get the possibility of additional efficiency, even without thinking about any of the multi-agent optimization or any of the additional things that we can do with this autonomous platform. So this is the basic idea. And so for the rest of the talk, what I'm going to do is I'm going to go through kind of the three components of the system. And since there are three PIs, there's a very obvious split in terms of these components. So the hardware design and the system design, that's led by Chin at WSU CPath. In-Orchard navigation is led by Matt Taylor at the Washington State main campus. And then my group is focusing on the multi-agent optimization. And again, this is a highly collaborative project. So of course, we have crossover between these different areas. So with that, what I'm going to do for the rest of the webinar is basically go through each of these three different sub-areas of the Bin-Dog and give you guys an idea of what we've developed here and what we need to move forward with in the future. So here's the hardware platform under a bit more of a microscope. We have passive suspension and a front axle pivot structure. One particularly interesting thing is that we have a four-wheel independent steering system. And so I'll talk more about that in future slides. But the idea there is that the wheels can actually move independently. So we can do Ackerman steering, we can do four-wheel coordinated steering, the vehicle can spin in place. And what that allows us to do is it allows us to operate the vehicle in some fairly close quarters. So if you're in a lane, you have a human that you need to avoid, or you have a tight headland environment where you need to operate, you can do that more efficiently with this four-wheel independent steering system. This is a gas engine powered vehicle, and it has a hydraulic system for the bin lifting component, and I'll talk more about that. And so the bin loading system has this scissors structure that we'll see more of as we look at a few more videos. So here's the specifications. Basically, it's about a 2.1 meter tall vehicle. So it's about a little bit taller than most humans. 1.5 meter track, 2 meter wheelbase, 9.6 kilowatts of engine power. So this is a fairly powerful vehicle, particularly compared to some of the ground vehicles that I've worked with in the past. Max speed is 1.2 meters per second. Which is reasonably fast. It's perhaps not as fast as a human in a tractor, but because of the advantages that we have of being able to go over the bin, we make up for a lot of that, and we also make up for a lot of that in terms of optimizing the efficiency. And there's also the possibility that we may be able to increase that maximum speed in the future. Maximum steering speed, 30 degrees per second, and it can pick up a 500-kilogram bin. So these bins are heavy things, but the hydraulic system is designed to handle that. So talking a little bit more about this four-wheel independent steering system that I alluded to earlier, we have 4 different modes that we can operate in on the steering system. We have Ackerman steering, which is what you would see from a car-like vehicle, so all of us are probably familiar with that. We also have four-wheel coordinated steering, which means that we can actually change the back wheels so that we can modify the pivot point. I'll show you a picture of that in the next slide. Crab steering, where we can actually put the wheels in different configurations, and that allows us to move almost omnidirectionally with the vehicle if we need to do so in very tight quarters. And then the spin configuration, where the vehicle can spin in place and potentially reposition itself if it's in a situation that it's not able to get out of with the other steering modes. So one interesting thing here that we've really only scratched the surface on is how do you combine these steering modes intelligently in the navigation system so that you maximize your navigation efficiency, and that's something that we're looking at. So just another visualization of these steering modes for the independent steering system. With the coordinated steering, you can see that you can position those wheels such that they pivot along that eye point there that is, I don't know if you can see my cursor, but right along basically to the right of the vehicle. With the spinning, obviously you can pivot around the center of the vehicle. Ackerman steering pivots around that point that is perpendicular to the back wheels. And then with crab steering, you can really move in a number of different directions if you so desire. So this is a really interesting design here, and it really is beneficial for these orchard environments where you sometimes run into situations where you're in very close quarters. So the control system for the vehicle, we allow for both manual and automatic control, so the vehicle can be joysticked by a grower or by a picker or a human operator if that's the mode that is desired. And then we're working on the automated control, and we have some results on that I'll be discussing in the second section. But essentially what the remote controller or the navigation controller do is they go into the same coordinate control system that then feeds into a fairly traditional PID controller on the wheel encoders. And so we have integrated the laser scanner and IMU and GPS technology into this navigation system, and that basically goes into the estimation portion. But that is at a different level, which I'll show the diagram later, than this coordinated control system, which basically allows us for both manual and automatic operation, which is something that was definitely a priority when we were designing the vehicle. So let's take a look at a field test here. And so I'll play this video a couple times since it moves through things fairly quickly. But so here we have spinning mode. It's now entering the lane. This is all under manual control. And you can see how the vehicle is able to enter the lane, drive over a bin, then move to the other bin, place that bin down, and then load. So you can see how it is now then able to drive back over there and then pick up this other bin all in one pass of the lane. And so this is not something that you're able to do with the forklift model. So let's just see that again. So loading the empty bin in the headland, entering the tree lane using one of its navigation modes. You can see the gas-powered engine there on the back and also the onboard computing, though obviously in the final prototype we'd want to have that be more contained, but this is just a experimental platform right now. Here we see where it's able to lift that hydraulic system up to move over the bins, which is really, really quite neat and interesting idea, and then basically pick up that other bin. So we basically get this sort of full bin management system going on without having to do multiple passes at the lane. So the navigation system itself, we also have GPS and IMU. We've also integrated laser scanners into this system as well. And so with the GPS and the IMU, we're able to do pure pursuit to do navigation. So if we have a trajectory that we'd like the vehicle to follow, we can decide whether we want to use Ackerman steering or the coordinated steering or any of those steering modes. And then the controller will be able to follow that trajectory. And so what we did recently was we ran a number of trials such that we tried to characterize the navigation performance of this vehicle in the real orchard environments. So here's some path tracking performance where the vehicle is navigating in the headland. So we just do a number of curves here with different offsets, so 5 meter, 6 meter, 7.5 meter, and 10 meter offset curves. You can see those on the different images. And then we execute those, and with the GPS and the IMU in the headland, we're able to get a pretty good idea of how well we've been able to execute those curves in terms of testing the controller. And what we see is that we get our offsets with the Ackerman steering for the tight curves about 0.4 meters, and then a little bit lower for the larger curves. Then with the coordinated steering, we're actually able to get lower values. So our mean offset in terms of the trajectory is now reduced to about 0.15, or even in some cases below 0.1 meters. So this is fairly nice precision controller in terms of being able to maneuver and track these trajectories intelligently. And so one thing that's really interesting about this vehicle that we've really just only scratched the surface on is how to combine these steering modes. So if I'm trying to do something like this 90-degree turn here where I start at point A and then I take a sharp left, if I just use four-wheel coordinated steering, I have to, if I'm turning into a tight lane environment from the headland, then I have to basically I have to do this little overshoot with the vehicle so that the vehicle then comes back into the lane in order to do this without running into the sides of the lane. But what I can do is I can combine multiple steering modes to reduce the space requirement and navigate in the more crowded orchards. So if I use crab steering to move from A to B and basically get on this trajectory, I can then use Ackerman steering for the easy part, spin, and then end with Ackerman steering again, and then I can the vehicle will give me a more tight following of this trajectory. And so this was an actual trial that we ran on the vehicle. And so something that we're very interested in, and we haven't quite figured out how to do yet, is how to automatically determine between these modes. And so that's actually a motion planning problem that is sort of future down the line. Okay, so also just to get you an idea of how long it takes for this vehicle to actually pick up these bins. So under manual control, looking at the bin loading performance, in the headland where you obviously have more space, so things are easier, you can pick up the bin in about 14 seconds. And then in the tree rows, you can pick up the bin in about 22 seconds. And so what we would like is we would like for the autonomous system to be able to get performance similar to what we can do with the manual control. But this is fairly reasonable in terms of time periods for your standard bin management in the orchard. So with that, I'm going to move on from hardware design and talking about what the hardware in the vehicle can do, and now talk a bit about the in-orchard navigation. And so this is the case where rather than trying to follow some predefined trajectory, assuming that we have GPS and IMU, when we go in the lane, we run into more cluttered situations where there could be GPS dropouts and we really can't rely on that global positioning system in order to do the navigation. So we need to think about the types of systems that roboticists are more familiar with in order to do these kinds of in-orchard navigation. So the system architecture for the navigation system, we use Robot Operating System, or ROS. So we're able to leverage all of the control, estimation, and motion planning capabilities of ROS. That navigation control goes to that low-level controller that I talked about at the beginning, and then gives you basically runtime feedback on what the vehicle is doing. We have GPS, we have laser, we also can integrate ultrasonic sensors and bring that sensor data back to ROS. And then the ROS does not interface directly with the mechanical system, but it does interface directly with the sensors. And then that low-level control system is what interfaces with both ROS and the mechanical system. And so this was a very deliberate design decision because we wanted to allow for that manual control component if we wanted to take out the autonomy of the system. So just last month in February, we went down to the orchard and we looked at how do we do, can we do laser-based localization? What kind of accuracy can we get with laser-based localization in these tree rows? And so this is actually a more difficult situation than you would typically run into during harvest time, because as you can see, the trees don't have a whole lot on them in terms of leaves or fruit. And so what we want to do is see, well, can we do localization within these rows? How good of an estimate can we get of the vehicle's position if we're trying to basically operate in these more challenging environments? So here are the results from the test that we ran in last month. So despite this feature poor environment, we are still able to get fairly precise precision with the laser scanner. So if we look at plus or minus 20-degree heading and then also 0-degree heading, we're looking at about 0.3 degree average deviation from the center point on the lane, and this is averaged over about 100 trials. And then the offset that we're looking at for the accuracy of the localization system sitting in the middle of that lane, get an average deviation of about 0.02 meters. So this is quite nice accuracy numbers in terms of what we're able to achieve, even in a situation where the features in the environment are not particularly rich. So we'd also like to see how accurately can we track a trajectory when we are using this navigation system. So now what we want to do is we have the situation where we are GPS denied, we're in the lane, and we want to be able to drive straight down that lane, obviously without running into the sides of the lane, but also to maintain that center track as much as possible. So our heading angle is basically how far off of 90 degrees we are, and then our offset is that center point of the vehicle, how close does that come. So our navigation trajectory, we looked at this with some different driving speeds. So for 0.3 meters per second through 1 meter per second, looking at the actual average speed achieved. So the controller is actually able to achieve close to this desired speed, maybe a little bit less in the 1 meter per second case. And we're able to get offsets from the center of the lane on average as low as 0.04 and as high as 0.07. But then our maximum offset, even in the worst case, is only about 0.2 meters from the center of that lane. So basically the conclusion here of these trials is that we're able to achieve a fairly high driving speed and also maintain a smooth trajectory with this vehicle. And so this really, I think, bodes well for being able to actually utilize this vehicle in the challenging orchard environment. So looking at the steering mode integration, we have been able to integrate multiple steering modes to smooth this trajectory. This is something that I alluded to earlier. Here we have the blue line where we're using both Ackerman and Crab steering combined. And then for the green line, we're using just Ackerman steering. And the decision to use Ackerman and Crab steering here is made by the system, but it's basically uses Crab steering if it gets far off of that center line position. So there's a threshold there. So this could be done potentially more intelligently even than this. But you can see that by combining those steering modes, we're able to smooth out some of those outliers. So particularly that big position error there at about 20 meters, we're able to smooth that over by taking advantage of the different steering modes of the system. So another autonomous requirement here is to actually find the bins and track the bins in order to be able to precisely move over them. And so in order to do this, we need to be able to do bin tracking to about 0.1 meters. That's about the tolerance that the vehicle has in terms of whether or not it can kind of bounce that bin around to the point where it'll get on the hydraulic component. And so our initial trials showed that we could just use fairly simple techniques like huff transforms, because the bin comes out very nicely in the laser scanner as a line in the middle of the orchard that is perpendicular from the lane. So using fairly simple computer vision techniques, we're actually able to get that level of precision that we need. So again, in these tests, We have the bin model identification. It does appear to be fairly robust, and we're looking at bin tracking errors that are less than about 0.1 meters, and that's our baseline in terms of what we expect to be able to do to be able to pick up that bin. And so we have picked up the bins autonomously at this point, but we have not yet done the trials to figure out how robust that bin pickup is. So that's one of the things that we have going on down the line. I should mention that we've completed about 1.5 years of this project, so we're about halfway through the 3-year National Robotics Initiative project. Okay, so that brings us to the point where we've talked about the hardware design and also the in-orchard navigation system that takes advantage of the laser-based localization. And so the last component of the talk today is the multi-agent optimization, and this is what my group has been working on. And what this basically is saying is, let's look ahead. Right now we have one bin-dog prototype, but if we have multiple bin-dog prototypes, or multiple within one orchard, can we coordinate them in such a way that we will optimize the bin management and improve this efficiency? And so what this is sort of a use case test of what kinds of performance we're going to be able to get once the system scales up. So here's the simulation environment that we developed. It's still fairly small, but the methods that we're developing are scalable. This was meant to be sort of a representative test case for a fairly small orchard within the Prosser environment. So we have 10 trees and 5 lanes. Workers average about 2 minutes to finish one tree, and that's from real data from real pickers. The robots move about 0.5 meter per second when carrying a full bin and 1 meter per second otherwise. This is based on the actual values of how fast the bin management robot moves. And so what we want to do is we want to be able to optimize where these bin dogs go to pick up these bins and to manage the bin management in this orchard. So the setup is we have groups of workers that are initialized at the beginning of the lanes in the headlands. If there are no more apples, then the workers will move to a new location and they'll request a new bin from the vehicles. Here we're assuming that the vehicles know where the bins are at all times. This could be done with RFID or a wireless network. The robots choose which bin to pick up, and they wait if the target bin is not full yet. And then the robots choose where to carry that new bin to, and typically that'll be to the depositing station if the bin is full. So we looked at a couple of different algorithms for doing this. The first algorithm is a fairly naive, greedy algorithm where there's no coordination between the bin dogs. And so here the bin managing robots will just choose the closest full bin or the earliest requested location. If there is no full bin, they'll choose the bin that they think will be filled the fastest, and then wait for that target bin to become full, and then take it back to the repository. And so there's no priority scheme here. Other robots cannot see these bin requests, and so they can't manage the requests. And so this leads to some inefficiencies in the sense that we now have the bin dogs waiting in order to figure out whether or not they should, rather than going to a bin that could lead to a more efficient strategy. So what we developed here was an auction-based method, and so it's designed to be run, you can run it in either a centralized or a decentralized way. We may not have guarantees on full communication in the orchard at all times, so we may need to look at need to have a decentralized approach, but this method will work whether you have a centralized auction or a decentralized auction. And so the robots coordinate through this auction, so each robot makes plans to pick up the bins in the orchard, and that plan cost is represented by the time required to reach that target bin plus the time required to wait for the target bin to be full. So both of those components are taken into account in essentially what the robots are doing is bidding for that bin task. And then the bin with the least cost, basically the bin dog with the least cost then wins the task and is able to then go and proceed to pick up that bin. So what does this look like? So here's the simulation. So here we have 2 bin managing robots and the 4 pickers that are moving down the lane. Some of the pickers are moving more quickly than others, and there you see that go over the bin strategy, where the bin dog is able to actually pick up the full bin and also drop off a empty bin all at the same time. And so here the robots are actually deciding which lane to move into in such a way that they can minimize the time that these pickers spend waiting because they're in a lane with a full bin. So this gives you some idea of kind of the improvements in efficiency that you would get versus a human in a tractor that would use a strategy much like the greedy strategy, where they would go to whichever bin is being called out without doing any efficiency optimization like we're doing here. And so as you can imagine, eventually we complete the harvest process in this orchard. And what we see from looking at the quantitative results is that by doing that coordination between vehicles, which is something that you really wouldn't be able to do in the traditional way of doing orchard management, we're actually able to reduce the total steps that it takes, or the amount of time, number of minutes it takes to finish picking the trees in this orchard, from about 1,000 minutes to 700 minutes. And so there you're seeing about a 30% improvement, and this is very much in line with our initial preliminary studies that said you could get up to a 50% improvement. And so again, this is not a perfect simulation, but we tried to make it as realistic as we could to try to show what kind of potential benefit we would get. And you see that as the number of bin management robots increases, we're still seeing fairly significant gains. And then on the right graph there, if you look at the number of bins retrieved for a fixed amount of time, so for instance, if you have to pay your workers for 3 hours, then you're getting close to a 50% improvement in efficiency there. So these are definitely very encouraging initial results, and I'm excited to see what we can achieve if we have multiple prototypes in the orchards and try to improve basically save these growers money for the bin management task. So that's most of what I wanted to talk about today. We hit the hardware design, we hit the in-orchard navigation, and then we also hit the multi-agent optimization components. Just for basically with the next 5 minutes or so, I'm going to go into some of the challenges that we're looking at now and the future directions that we have on this project for the next year and a half and then potentially beyond if we continue this line of work. So the next steps in terms of navigation, one of the issues is speed limitations on the current platform, and so that's a hardware limitation. It certainly would be beneficial to have the vehicle move more quickly. This ties right into the safe operation with humans. If we have these fast-moving autonomous vehicles moving with the pickers, this could potentially lead to injuries and hazardous situations. So all of the issues that folks are looking at in robotics in terms of robots operating in human workspaces, this really comes into play here as well, which was part of the tie into the National Robotics Initiative. Here was that idea of safe operation with humans. Low-level control of the steering modes or automatic control of those steering modes, trying to decide which steering mode to use to try to improve that efficiency. And then also the idea of how does the perception change across seasons. So if you're doing harvest time, really this system is designed for harvest time, but if you need to navigate in the orchard in non-harvest time, are there differences that you have to make for the navigation system? Can you use the same techniques depending on how the lanes look like? And so what that can help us move towards is sort of more robust navigation systems for different kinds of environments. On the multi-agent optimization end, we can think about a few different extensions there. So the idea of moving semi-full bins to optimize performance, that's not something that our current approach does. Now we tried doing that, and what we found is that we weren't really able to get very substantial gains in efficiency by moving those semi-full bins. And so there's some question as to whether or not there's really a lot of utility in that, because obviously it takes time from the bin management robots. But if you had a large number of them, then there could potentially be benefit from that. So that's something that we're looking at. Also, this big question of how to balance the workload to make sure that vehicles are not waiting and that all of the vehicles are doing effective bin management at all times. That's something that we would certainly like to deal with. There's also the matter that workers work at different speeds, so is there an advantage to basically learning how quick some of the pickers are and taking advantage of that information and relaying that to the robots and having them change their bin picking strategies based on that? And so that's something else that we're looking into, and that might require some additional learning approaches to try to figure out how to optimize in those kinds of situations. So with that, let me just acknowledge all of the other folks who've been working on this project, students from WSU, Washington State University, and also Oregon State University. There are 4 students who've worked on this project, 2 senior personnel, both at OSU and WSU, and then the PIs again are Chin Zhang, Matt Taylor, and myself. And then, of course, thank you to the National Robotics Initiative and the USDA for the funding. And so I'll also thank you for coming and take any questions that people might have.
Jeff, thank you very much. This is wonderful. This is a huge reminder to us who do robotics, especially agricultural robotics, that it really is not only about what we call the robot, right, the motors and the computer and some software, but there are so many components to make a system successful. And it was a great presentation, very, very comprehensive. Thank you very much.
Thank you.
Let me open up the microphone for folks to ask questions. And while people are warming up, if I may start, you touched upon briefly here at the end talking about navigation outside of the harvesting season.
Mm-hmm.
But in fact, one of the issues that we've heard from growers when we were developing autonomous orchard vehicles is how do you leverage that technology year-round as opposed to something that you buy only for harvest season for 3-4 months, and then the other 8-9 months of the year is sitting in the garage and your investment is not being well used.
Mm-hmm.
Do you have a chance to discuss this and possible other uses of the technology outside of harvesting?
Yeah, that's actually a great question, and I'm going to have to think on the fly because, no, we haven't really thought too much about that, but this is definitely something that comes up. We've also been talking to vineyards as well, not about Bin-Dog, but about other agricultural robotics applications, and they say, they have this harvesting equipment that literally sits in their garage for 10 months out of the year. And so thinking about other potential uses of these kinds of systems, you could use them for monitoring. If you want to, you can because they have a fairly nice suite of sensors. So if you wanted to go around and get an idea of what the water levels in the orchard were, or any other of those quantities of interest, you could have a surveillance robot going around and doing that. And with the autonomous navigation capabilities, you could then try to optimize that survey or that surveillance. That would be another possibility. I don't know how useful that would be, but in some cases it seems like that information might be something that they'd want to know.
Absolutely. Anything that you can find that can reuse that machine throughout the year will certainly go a long way to making the economic case for the machine more reasonable. Yeah,
absolutely. And that's always tricky with these kinds of things is whether or not it is actually going to be economically feasible to do this.
Mm-hmm. We have a question from Carrick at the University of Nebraska-Lincoln. It's on the chat window if you want to check it out.
All right. So surprises in the first field tests. Actually, honestly, the surprise in the first field test was that it worked better than we expected. So we had developed this navigation system and with the laser scanner and moving down the row, and we were really surprised that it was able to do that without any leaves or any apples on the tree. And so just the bare trees was sufficient to actually be able to do a fairly precise localization. So that was one very pleasant surprise. The other thing that was, thanks, Carrick. One other thing that was interesting there was that it there's actually there's a higher level motion planning problem involved here too, because it's not just that we want to turn into the headland, but we actually want to do that in a way that we can sort of minimize that arc and minimize that overshoot, and also do it in such a way that the vehicle doesn't surprise the pickers, because some of those movements that you could potentially make, you don't want them to be surprising, and you don't want people to be intimidated by the robot or be unhappy to be in the same space with the robot. So that was another thing that we noticed, was that we really have to be careful in terms of making these movements such that the humans are not surprised by them.
Yeah, that makes a lot of sense. So you said you're halfway through a 3-year, correct?
Yes.
Nice. If I may ask, on the last day of the project, when the sponsors come in to see the result of their investment, what do you envision will be like that big final demonstration or experiment?
Yeah. So I think by the end of this project, we want to have the robot operating fully autonomously. So being able to drive in the orchard, drive through the lanes, navigate in the headlands, pick up the bins, drive over the bins, and be able to do that all in an automated way. So just that full demonstration of a single platform. I don't think by the end of this project, really within the scope of this project, we're just going to have one of these guys. So being able to show the benefits of the optimization and being able to, and the multi-agent coordination, that's something that I think is still going to be in simulation. But what we'd like to have is show, here is the proof of concept that this vehicle works and that we can do this autonomously. And then the next steps are going to be to think about, so is this commercially viable? How many of these are the growers going to want and need? What's the service model for this? Is this something that they can rent, right? And what's sort of the way of pushing this forward?
Yeah, these are questions we already got. What's the economic model?
Yeah,
and having that at least in some draft form is a great idea. Yeah,
so that's something that I know that Chin is definitely thinking about very carefully.
Mm-hmm.
So I kind of depend on him for that because of his connections with the growers and his closer connections in Prosser to what's going on with the in terms of the economic implications.
Very nice. Yeah. Any other questions, anyone? Jeff, thank you again very much for the presentation. At least here at CMU, the Bin-Dog was always a concept in a lot of people's minds, and it's a real pleasure to see that someone is taking this to reality. Good job.
Yeah,
thank you very much.
Thank you so much, Marcel.
And everybody, we are going to see you next on April 28th at 2 p.m. U.S. Eastern Time. And details about our next talk are coming up soon. Everybody save the date, and I'll see you soon. Thank you again. Bye-bye.